In the graduate session, I talked about the solution to the general linear model. And then we talked about after we've got so we first get the solution to sort of get our hemodynamic response function, solve for the hemodynamic response function. And then how do we calculate a significance from that, which involves trying to figure out how much of the variance in the voxel time course could be explained by our experimental design. And if none of it can be explained by the experimental design, well, then we'd say that that voxel didn't respond. It still responded in the sense that it went up and down, but it didn't respond to what we did. It didn't correlate at all with what we did. So, so to start off with, what do I mean by linear? So let's just back up and just say, what does it mean to be linear? And so the definition of something being linear is a very simple one. So if this f is a linear function, then the following will be true. So if it's a linear function, then if we operate that linear function on some argument, and then we add it to operating on a different argument, then that will be equal to operating the linear function on the sum of the arguments. So that's all that. So that's the general definition of linear across many dimensions. But let's just take like a very simple, a couple simple examples of what's linear and what's nonlinear. So when you look at that definition, when you first write it up, it's kind of like, it doesn't do it for me initially. But let's just apply it to a simple case. So the absolutely simplest case is, just a line. That's linear, right? So if here's, say, point A and point B. So if we go up to point A and then calculate, run it through the function, then we get f of A. So that's f of A. And then we go up to point B, run that through the function, then we get f of B. And so what is f of A plus B? Well, here's A plus B. So if we look at A plus B, it's going to be so here's A plus B. So we'll get something up here. And that will be equal to f of A plus B. So, sorry, I drew this. Let me draw this again. So, what's f of A plus B? It's not what I drew there. So here's A, and here's B. So let's add A onto B. Okay, so here. That's better, Marty. Okay, so this is A plus B. Okay, and so if we go up and find that, and we go over and look at f of A plus B, you can see that this is, you can just work it out with a simple line, like a slope of 0.5. So, you could do the same thing with, this is like, y equals, 0.5 times x. Something like that. So that will apply to any possible A and B. If you can show that it applies to any possible A and B, then you have a linear function. And what it means is if you operate on A and then operate on B and then operate on A plus B, it's the same as adding up A plus B. So this should be A plus B should add up to f of A plus B. So what's an example of not a linear function? Well, a lot of different things. So an example could be something like anything that's not straight. So let's just take one example, like say inverse tangent. What does that look like? That looks like something that sort of comes like this, goes through 0, goes like that. So that's not linear. So it goes up to 1 and minus 1. And so why isn't it linear? Well, if we take say go out here, and we get that number on the y-axis, and then if we say go out here, and we get that number on the y-axis, what is our prediction of adding those two together? So if we add this guy onto this guy, we would go out to here. And so what would our linear projection be? It would be adding this one onto that one. So we would add, so our linear projection would be up here. This is what our, that's what I would expect to be if it was linear. But it's not linear because it's actually down here. So our brain response is linear? Not even vaguely. So, an example is of something like this is, what if you show somebody a face and look at the brain response and you show them the exact same face again? In virtually all cases, there's going to be less response when you show that face the second time. There'll be some habituation. So any kind of habituation is not linear. And our whole assumption of doing our analysis, so this guy is linear. Y equals tangent of x, not linear. Our whole assumption of the general linear model, which majority of fMRI data is analyzed with, is not true. We know it's not true, but why do we do it? Because it's well understood. How it fails is relatively well understood, and it's hard enough. If you went to the 8 a.m. lecture, you say, oh man, that's kind of a nightmare just for simple linear. But what are we assuming when we assume that things are linear? We're assuming that responses just add to each other. So if you do like a flash, like a short visual flash, not flash sequence, but short visual flash, we can measure, you could do that a whole bunch of times with a lot of space in between and measure the hemodynamic response function, which is our impulse response function. So that's an impulse response function. And what does that mean? That means that if the system is linear, this is all we need to do. And once we've done that, then what we can do is, if we have some arbitrary stimulus, like say 2 flashes, then we can predict what the response is going to be without having to measure it. So what is the response going to be? Well, we're going to trigger off that hemodynamic response function, and if we hadn't done anything else, it would have just died away. But now we've got another one, and we'll just trigger it off again, on top of that, and then they'll both die off. So that's what the general linear model assumes. It assumes that whenever you do something, the brain responds, and then if you do something again, the brain just adds activity onto whatever ongoing activity is already there in the brain. And like I said, we know that's not true, but that's the way we analyze the data. And we do that because it's hard enough. If we allowed for all different kinds of nonlinear effects, that greatly complicates our analysis. And one of the advantages of linear systems analysis is that it's well understood, and its failings are well understood as well. But that's our basic assumption. And it is approximately true. So if you go to, say, visual cortex and do 2 flashes that are shorter in spacing than the spacing of the hemodynamic response function, you'll tend to get something that looks sort of more or less like this. This is like actual data from V1. So in certain early visual areas with very simple stimuli, this is approximately true. It's probably not generally true across the brain, but we just analyze things that way because it's simple and well understood. Okay, so any questions about sort of basic idea of linear? It just means that all your different effects are just adding on to each other without interacting with them. With different things interacting with different things. They just linearly pile up on top. They just add. So if we make that sort of strikingly wrong, but approximate assumption, then we can write out our general linear model. And so we'll write it out here. So our vector of data at a single voxel. So what does that mean? That means it's a time series of brightnesses of a single voxel. So the whole thing we're doing here is just voxel by voxel. So that was one data point from a brain image, just at one voxel, maybe 400 time points, and so we just have 400 brightnesses. It's just a curve going up and down like that, say like about 400 count. So that's our data, and we're explaining it by several things. And so the first thing is an experimental design matrix. That's actually what we did, like we turned on some faces and then turned off some faces. So the first question is, why is it a matrix? And it turns out it's a matrix because we're going to convolve it with our hemodynamic response function. And when we do a convolution, for each point in the output of a convolution, you've got to take a bunch of numbers and multiply them by, piecewise by another set of numbers in the hemodynamic response function, sum the whole thing up, and you get one data point. So to do that operation, you need a matrix. So each data point in in our explained data is going to equal the hemodynamic response function times a bunch of different points in this experimental design matrix. So we're going to do the convolution by essentially writing the convolution into the experimental design matrix. And I'll write out explicitly what that looks like. And so this thing is basically that x times this hemodynamic response function vector is basically a convolution. So we're writing out a convolution just as a vector equation of a vector equals matrix times vector. So that's part of what goes into the data. And then another thing that goes into the data is our nuisance vectors. And our nuisance vectors, and we can have multiple ones, so then it turns into a nuisance matrix, are things that actually occurred but that we don't care about. So a classic example is something like a movement artifact. So a movement artifact will strongly affect the data, generate a signal in our time series here. It's a real thing that occurred, some motion occurred, but we don't care about it. We want to sort of subtract it out. And there might be, so it could be just a very simple drift. So like, say here's your data, and you look at fMRI data, and it sort of does something like that. So that's an example of a linear drift, and we could say, well, that kind of looks like a line, so why don't I subtract out that line and then get what I really want, which is the data sort of like that, so that I can sort of analyze it without this artifactual drift in, maybe due to movement, or maybe the scanner is a little unstable and it makes the image slightly brighter over time. So that's an example of a nuisance variable. It's something it's a real thing that we just are not interested in, or we explicitly want to ignore or subtract out. So, and there might be multiple ones. There might be, a linear drift, or there might be something like this where your head went back, and then later in the experiment your head came back up again, or maybe it looks something like that, where your head went back and then it came up and then it went back again. So all of those things we want to get rid of, and so there might be multiple ones, all linearly added to each other. And so here's a set of weights for those different nuisance time courses. And so these two things added together are the sum total set of different time courses that we can explain. But your brain might have been doing something else. Maybe your brain, like I said in the last lecture, maybe you were thinking about what you're going to have for lunch, and that caused some brain activity. Whereas your experimental design was, no face, face, no face, face. And so maybe what you were doing was halfway through the experiment, I started thinking about lunch. And that caused some voxel somewhere to become active. You're not going to be able to explain why that voxel became active, because it will be active, sometimes when the faces are on, sometimes when the faces are off. It's not correlated with them at all. It's just because you were thinking about lunch. And so then we have to add some error or noise. So here's some noise, and that's basically parts of the time course that we can't explain with either what we did in the experiment or what we did, or some nuisance variables like a linear drift. So that's our first equation. We'll just label all those. So this guy is our data. And so that's single voxel time course. This guy is our experimental design. And this is basically a written out convolution. So that's a convolution. Written out discrete convolution. This is what we're solving for. This is our hemodynamic response function. So that's, if we just have one condition, it's just like, what did the response look like over time at that condition? These guys are the nuisance time courses. Like linear drift. These are the weights. How much of each one of those are we adding in there? And then finally, this is the noise or error. And that's basically stuff that the brain did that we can't explain by our experimental design or some kind of drift. So what does that look like? So if we draw it out sort of explicitly, so we start off here. So we've got a long vector. So now we're just going to draw. So here's our y vector. So what's in that y vector? It's just the brightnesses of a single voxel. And so this is the time of the experiment going that way. So it's important to sort of keep in mind what the dimensions of these matrices are. So that's the time of the experiment. And then we're saying that, so I mean, if you look at this equation, what it says is, when you operate a matrix on a vector, that gives you a vector. So x times the hemodynamic response function vector is a vector, plus the S matrix times the weights vector is another vector, plus the noise is a vector. So the whole thing is a vector, just added up, linearly added up. So now let's look at what that X matrix looks like. And let's just do one. So what are we illustrating here? We're just illustrating the most brain-dead possible experiment, which is we turned the stimulus on and then we turned it off. Okay, so that's time. And this is 0 and 1. So we turned the stimulus on, turned it off. That's it. And so how do we convolve that with an unknown hemodynamic response function? And so how we do that is, I'll just draw out some of the matrix. So what are the dimensions of this matrix? So the dimensions of this matrix are the time of the experiment going this way, and the time of the hemodynamic response function going this way. So how do we illustrate this simple experimental design? This is just a one-dimensional experimental design. So what's the second dimension? The second dimension is just allowing us to do the convolution. And remember, the convolution involves taking the hemodynamic response function, flipping it around, and then multiplying each number in the hemodynamic response function times the number in the thing you're convolving with, adding up that whole mess into a single number. And so let's look. Let's turn the experiment on for, say, that many times, and then it'll be zeros after that. I won't draw all the rest of the zeros. So the way you write out a convolution with a matrix is we just sort of displace the ones like this. So this is how we convolve how we essentially write out a convolution with the matrix. Okay, so we'll just leave it there. So we just got one condition, and it's all zeros. And so that's our experimental design matrix. So X, that's our X matrix. And now what we're doing is we're multiplying that by our hemodynamic response function. Now, what is the size of this guy? This guy's going to be shorter. It might be, say, like 10. So this is our H vector. So that one is going to be the same size as this part of the matrix. And so basically, at the very first time point, what is the value of the convolution? It's going to be 1 times whatever the first number in your hemodynamic response function is, and then 0 times all the rest of because there hasn't been much chance for something to happen. Whereas if you go down a little bit later in the experiment, you're going to be touching more of the hemodynamic response function. And so you'll multiply, all these ones times the values in the hemodynamic response function. If you work it out, it's basically just it's just a discrete convolution. It's just the way to do the convolution the way we described, you take your hemodynamic response function, reverse it, plop it down at the time point you want to, or so like this. You want to figure out what's going on at a particular time point, reverse it, and then look at what your experimental design matrix was, and multiply those guys, add up the whole thing. That's what it's doing. Okay, so I'll take those zeros out and just assume 0. Everything else 0. So this is the same dimension again. This is the time of the hemodynamic response function, and that's an unknown. So that's one of the things we're solving for, because we don't know what it is. And then we've got another thing added on to that, which is our matrix of time courses. And so we could have like a time course, we could have a linear ramp in here, like -1, blah, 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 0, +1. That would, sorry, this needs to be a matrix. So that can also explain some of the data, because we know that, linear ramps can occur. And then, we might have, say, a quadratic ramp, some kind of like lump. We could code out a lump with a bunch of numbers. And so this, again, is time of the experiment going this way. But now what's going this way are the number of factors that we have going that way. So that's linear ramp is one factor. A little bump, like quadratics kind of thing, is another factor. So that's going to be, so there'll be another, maybe this is coding for a little bump. This one's coding for sort of like an up and down bump, So those are all our different factors, and those will be multiplied by a smaller matrix, a smaller vector, which is the weights for each of those factors, also an unknown. So that's a B there. So that's our weights for each of those nuisance factors. And then finally we've got our noise vector. And so and that also, so that noise vector is whatever, it's our error vector basically, whatever we couldn't explain for this actual time course. So this again, is time of the experiment going down this way. So that's the most brain dead experiment. We just turned something on, we turned it off, and this is how we represent it, how we represent the convolution. And what are we doing? We're trying to solve for. So basically, we're trying to solve for H. And so what is that? We call that deconvolution. And so how do we do that? So we've got the data. That's a known. We have the experimental design. That's a known. We have our nuisance expectation of what kind of nuisance things we have. That's another known. And we make some assumption about the noise and solve for the hemodynamic response function after maybe subtracting out some of these nuisance variables. Now, that doesn't look like a very good experiment, and so how could you have, you could easily see how you could expand this out for like turning the stimulus on again, but what about like more than one condition? So multiple conditions. So here's a dividing line. So what about multiple conditions? So the way you do that is we've got to extend our hemodynamic response vector, multiple conditions. Now, it's possible you could put two conditions on at the same time. That's not a problem because we're all linear, and so if you show somebody a face and a house at the same time, you ought to get sort of a linear sum of the face and the house. So what does the experimental design matrix look like if you do that? It's a little more complicated, but not too bad. So basically, we turn on one stimulus here, and now we're generating that discrete convolution of that stimulus. Now we could wait until until the first stimulus is off, or we could just turn on the second stimulus while the first one's still on. That's definitely possible. So that's our first stimulus, and maybe later on in time it might reappear, it could reappear later on in time. But now we've got a second stimulus, and we do that by sort of expanding the experimental design matrix, adding more columns to it. And so let's say this stimulus was still on, and we turned on another stimulus while that one was still on. We can do that if we want. And so this one's turned on later because this is the time of the experiment, remember? So this is the time of the experiment going this way. So that guy was still on. We turned on another one. And that could be like condition 2. So here's here's our X matrix, and this is condition 1. Let me put it down a little lower. So here's condition 1. Here's condition 2, etc. I could have more, because we need to have a separate hemodynamic response function for the different conditions. And so this guy right here is time in the hemodynamic response function HDR1, and this is time repeated again in the hemodynamic response function 2, etc. So that's how you would expand out the matrix to include multiple conditions. So that's going to require a longer hemodynamic response function vector and unknown. So now we're going to have one that is like 3 times as long, something like that. So here's H1 vector. That's for the first condition, because remember, it's always going to be, this middle part's always going to be multiplied by the middle columns here. And so here are the hemodynamic response function 2 for condition 2, etc. So basically, what is this going to look like once we solve for it? Well, it's going to look like, like here was the response to condition 1, like that. That's the hemodynamic response function sort of drawn out, and maybe the response to condition 2 was less. And so here's the smaller response to condition 2. Those are our unknowns. And then the other part is just the same, plus same. So we didn't change anything for our nuisance. The nuisance is still going to be there just like before. So that's how we could add multiple conditions to our experiment. So now, if you've read any papers about analysis of fMRI data, you'll see that there's often multiple different ways of writing out the same thing. So let's just write out a couple more, ways that you might see in the literature of what this looks like. So sometimes people just glom on the nuisance factors onto the experimental design matrix. That sort of simplifies. It makes less letters, and mathematicians always like less letters. And so, one thing they might do is you might see it just written out like this: our vector of data equals our experimental design matrix, prime, because now it's got the S in it, times our hemodynamic response function vector prime, because now it's got the weights, these weights in it also, plus the noise. So you might often see the same general linear model written out that way. And what's going on? So now we've got that one's the same. That's our data, and our data equals our experimental design matrix with the S matrix sort of tacked onto it. So that there's the Y vector, and here's this. So those matrices are the same number of rows in those matrices. And then you've got to do the same thing for the. So you've got your hemodynamic response function, but then you've tacked on the B underneath it like that, because those later ones are going to multiply the columns, the later columns. So so you might see it that way. So this is the H, and that's the B, and then the noise is the same. So plus the same noise. So it's not uncommon to see it that way. Noise vector. So basically that's just paste S onto X and B onto H. So, and there's certain reasons that we went over in the 8 a.m. lecture about why we might want to really treat these two matrices differently. But sometimes people just ignore those problems and just sort of paste them all together. But there's another simpler way that you might have seen, which simplifies the problem even more. And so one of the things that we're doing here originally is this idea of deconvolution. So we're trying to solve for these unknowns, these hemodynamic response function curves. And what does that mean? We're trying to sort of like, we're trying to find, it's discrete. So here's that rapidly rising first part, and then it falls off slower. So you're solving for maybe the hemodynamic response function might have 5 or 10 numbers in it, something like that. So what you're trying to solve for is you're trying to solve for that curve like that. And so you've got 10 or 20 unknowns, and those unknowns are across every repetition of the condition, a particular condition. So here you did the condition 1 once, and then you did the condition 1 later in the experiment a second time, but it's multiplied by the same hemodynamic response function 1. So you're solving for a hemodynamic response function that is across all the instances of one kind of a stimulus. So you've got a lot of data. It's possible to do this. We've got plenty of data to solve for those smaller number of numbers. But one thing you can do is, why don't we just sort of assume that we know what the hemodynamic response function looks like, and just solve for the amplitude of it. So an alternative thing is just assume we know shape of HDR, and just solve for amplitude. And what does that mean? That means, like, we could say that we know that the hemodynamic response function looks like that. And the only thing we don't know is just how high it was. It's always going to have that shape, but maybe it's low, or maybe it's actually negative. This voxel suppresses itself when something comes in. That's possible too. And so in this case, we're just solving for one number. So the idea is there's just one number, which is like what we multiply that hemodynamic response function by. So in this case, solve for amplitude, which is just one number. And you can do two numbers. There's different. We could say, like, what if we allow the hemodynamic response function to look like this, but maybe the peak could be a little later, so we could maybe solve for a second number. But basically, let's just do one. So sort of have it clear in the mind. So in this case, we're not solving for this whole shape of it, allowing each one of these numbers to vary independently. We just say that we know what it looks like, and all we're solving for is just how strong it was, or it could be negative. And so if we do that, then what we can do is we can pre-convolve this hemodynamic response function with our experimental design matrix and get rid of all the crap in the experimental design matrix and just have an experimental design vector. And so you'll often see the general linear model written out like this instead. And so what it looks like now is, here's our vector of time course points in our voxel, single voxel time course vector, brightnesses at each point in time in the experiment. And now what we've done is we've got now an experimental design vector. And what is that? That is basically, we just take our known hemodynamic response function and convolve it with. So now we know what that is, and so we can actually just multiply that experimental design matrix times our known hemodynamic response function and get a vector. So this guy's just a set of numbers, not a square, not a rectangular matrix. And now what we're doing is we're only solving for just the height. And so after we've convolved our standard height hemodynamic response function with our experimental design matrix, then we just multiply it by a number. So that beta is just a number, which which multiplies the height of that hemodynamic response function. So that's how you essentially solve for the height. So this guy is, this guy's just a number, not a vector. No, it's just the height. Unknown height. I should put that in there. So it's a unknown height. So you'll often see, if you hear beta, or in England beta, so if you hear beta, that's what that's referring to in this context. And then there'll be a noise vector, as there was before. And so when you look at it that way, you can see that it just looks, now you can see that's just a linear equation. That's just like, y equals, mx plus b. It's just a simple, that looks like, y equals slope times x plus the intercept. So you can see that's just a linear equation. It's not one linear equation, right? So that's one linear equation, but it's actually a whole set of linear equations. So it's y equals mx. So there's a whole bunch of different linear equations, one for each time point. So this is a whole set of simultaneous linear equations. But you can see it's kind of a linear thing, and so you got some data, and you're just basically trying to figure out you're just trying to fit a line to it. So that sort of brings it back to simplest sort of linear idea. Now, it's not uncommon, instead of messing around with the S, so since we're linear, this is the reason why everybody loves linear. So since we're linear, we can assume that our nuisance things can just be subtracted out. That's what linear means. So we can just try to figure out what the nuisance vector is, and then just subtract it out, linearly subtract it out. And so how would we, and so that's often done. So instead of explicitly modeling it and then trying to solve for what the weight, the weight of a particular linear nuisance activation is, we can just try to subtract it out before we even start. And so that's another common thing that is done. And so what does that look like? That looks like, here's our data. So, we've got, you were doing the experiment and showing a face, and then no face, and a face, and no face, and then suddenly somebody moved a little bit like that. So what do we do? Well, we just fit a line to that, and then just subtract out that line. Subtract out the value at each point on the line. Just subtract it off. And so if we do that, what will we get? We'll just get something that's around 0. So it will look like, this. Something like that, and maybe there was a movement. Make that movement a little less. So in this case, what we've done is, because everything's linear, we just subtract out, S effects, nuisance, before, from y. Remember, what we're looking at here, this is y, the y vector, and this is, y fixed. And so before we even get around to, solving for those, solve for, beta number. So before we solve for that beta number, remember that number is the same throughout all these copies of the linear equation. So this is a linear equation, but that's a vector, so there's a whole pile of them for each time point, but the beta is the same. The beta is the same for each different time point. And so, because it's just the height of the hemodynamic response function. So we're solving for the single number here across, multiple equations. But the idea is that once we fix this, then we just take this guy and stick it in here. So with the nuisance subtracted out of it. And that's opposed to doing it this way, where you have to separately solve for what the weights of the nuisance are. Okay, so that's the basic general linear model. And so now I'm building up to the 8 a.m. lecture. So how do we think about this? So the way we think about it is, we think about it as the experimental design defines basically a space of possible time courses. So the experimental design matrix, which you can, decide how you want to make it. One way of thinking about this is we can think about it as defining a space. Now, I've just drawn a two-dimensional space here, but what is this space? This is a space of time courses, and what on earth does that mean? So what it means is that each point in this space, each point, which you can sort of think of as a vector to that point. So each point, is a time course, a different time course. That's what it means to be a space of time courses. And so there's a whole bunch of different places in there. You can have vectors to all different places in there. And those vectors are, each one is a different possible time course. But the problem is, our data doesn't have to be in that space. So our data could stick up out of the space. It could have a different time course. Some of the data could be explained by the experimental design space. So this is our experimental design X space. But some other part of the data, here's the Y, the actual time course that we got, cannot be explained by the set of possible time courses that the experimental design matrix can explain. And so what do we need to do? We need to project that guy down into the plane and get that vector. So that's a right angle projection down into the plane. And what is that? That's the experimental design matrix times the hemodynamic response function. That's the part we can explain. It's not noise. And then what's this guy? This guy is the noise vector. So that's the part that we couldn't explain. So this is, couldn't explain this. That was like, thinking about your lunch. The voxel was going up and down. There was a bunch of variance in the voxel, but none of it correlated with your experimental design. So it couldn't explain this. So fundamentally, how do you analyze your data? What you want to find out is what's the ratio between those two. So you want to figure out, like an F ratio, or is there signal to noise ratio? Because if you explain a lot of, so you could have another situation where, like here's your experimental design space. So that's the set of possible time courses that we can explain with our experimental design. And say, your data looks like that. And maybe if you make a perpendicular projection, there's like a tiny bit of the data you can explain like that. But almost all of the data is perpendicular, meaning uncorrelated with your experimental design. And so in that case, you would say, so the vector, you could say this is like, not significant, right? Not significant response. It doesn't mean there wasn't a response, not significant response to X. In this case, it was a significant response to X. So that's how you calculate your significance of your response. You say, like, what is the ratio between how much of the data can I explain versus how much of the data could I not explain? So that's sort of fundamentally like a geometric picture of what we're doing here with this general linear model. And it's all involved with sort of right angles, things just adding to each other, all nice and simple. It sort of seems kind of complicated already, that's right, but nonlinear is way worse. So how do we sort of characterize this space? So we can characterize the space by just looking at the X matrix. So here's the X matrix. That's just, the ones and zeros of when the stimulus was on and when the stimulus was off. And if we look at the columns of that matrix, so the columns of that matrix represent the basis vectors for, X space of time courses. And I already said it in the ADM lecture, but just do it one more time. So let's just take now this might be, you might have a lot of columns there, like 100 columns or something. It's a 100-dimensional space. So that sort of seems very abstract. Let's just take a very concrete example. Say we have one column that has 0, 1 in it. And we have another column that has 1, 0 in it. So if we just think of a simple graph, we've got 0, 1, and 1, 0. So if those are perpendicular to each other, they're uncorrelated with each other, but we could have all different combinations of those because the hemodynamic response function, could multiply multiple ones. And so we could say, here's a response that we can explain. That response is equal to 2 times the first basis vector plus 2 times the second basis vector. So this is a space of different time courses. So, like, what does that time course look like? That time course looks like 2, 2, 2. So that's a time course that's actually in the space of possible spaces that we can explain. 1, 1 would be in there, 0, 1 would be in there, 1, 0 would be in there, all those other ones would be. Those are all this is the space of time courses. So what is an example of a time course that we can't explain? Well, we'll say there was another dimension of this space, sticking out at us like that. And say, we had a vector that was sort of coming out at us like that, sticking out in 3D, projecting down like that. That vector would have a component that was not explainable by this space. And that can happen. That's like thinking about lunch. That's causing the data vector to veer off into another dimension of possible time courses that you're not actually able to explain. So the experimental design matrix has a lot of information in it. It says, like, when you set up that matrix, it says, these are all the different possible time courses I can explain. And there's some that I can't, that are not in my space. And the data might include some of those. And so when we analyze the data, what we're trying to do is figure out how much can we explain versus how much can we not explain. And then that ratio will tell us whether we have a significant response or not. Because remember, there could be a lot of activity thinking about lunch, and our experimental design matrix is not going to explain that, but it's real activity. It's actual real activity in the brain, real variance. Okay, so questions about this? It's linear. It's linear and it's simple. It's just addition. It's just addition and multiplication. This is the basic way that we, analyze fMRI data. We assume everything just adds linearly on. The noise adds linearly on to the our response voxel. These nuisance variables just add linearly on to the response voxels. The conditions add linearly to each other. Within a condition, one condition, if you turn on that condition again before it's had a chance to die out, that just adds linearly on to the previous time you showed something. So conceptually, it's very simple. You're just assuming that whenever you do something, it causes a reliable brain response, and that brain response will just add on to whatever is currently going on. And like I said, of course, that's not true. There's all different kinds of habituation and all different kinds of additional effects, but this is like the first level analysis that you always run on your data. Okay. I didn't leave even a tiny little second for questions. Any questions at the last minute? Now, you don't have to do all this thing. You can just say, there's lots of software. You can just say, here's where I turned on the faces and here's where I turned off the faces. You make the experimental design matrix with all the convolution business in it. You don't have to do that. So all the software is set up to do that. All you need to do is just put in when were the faces on and when were the faces not on, and then you're done. But it's good to know what's, see your food, see what's actually in, what's actually going on under the hood. Okay, so any questions even going back to the very beginning about the general linear model? So if you look at the 8 a.m. lecture, you can see how you can sort of deal with this problem in more detail to actually calculate how you calculate an F ratio or a significance out of your data. This one's simple enough where you can almost understand it just right here, because you can just see you're solving for a beta, And that's the same beta for all the copies of this equation for each different time point in your y vector. And you can clearly see this is basically just a linear regression, a simple linear regression. Dealing with this whole mess is a little worse, but this is the most straightforward one. But it's related to this. It's basically the same thing. Okay, so any questions out there? You've probably been over something related in other statistics classes, because it's this same sort of basic formalism is used thousands of different places. So it's very, very common. Linear, everything linear just adds. Great. Okay, any last questions or first questions? Okay, I guess we'll call it a day. Hey.
Is there any kind of analysis like this where perhaps your models have, say, multiplicative effects rather than additive effects?
No, there aren't a lot. Yeah, there are a lot of people that have actually looked at clearly habituation takes place. Is there, can we model this? If you're just doing, if your experimental design is simple enough so that you can actually say like faces, for instance, what you could do is you could just do an event-related design and actually, solve separately for the hemodynamic response function for each presentation of the face. Or you could just average a bunch of cases like that. So present a whole series of faces and then average across subjects, first face versus second face versus third face, and then just see, is there a fall off? Yeah, so there's many different ways you could sort of go beyond just a simple, linear sum. They all involve, you can see they all involve more data. Because if you're allowing the hemodynamic response function to be different for each presentation of the face, well then you've got a whole bunch of unknowns. And so you've got a lot more unknowns, and then you're going to need more data. But people have done that. So you could do, if you just collect a whole bunch of data, enough data so you have some, significant clean, time courses across subjects, then you can do that. And people have done that. I'm not saying that there aren't any sort of nonlinear, analyses out there. It's just that this is kind of like the first crack that you almost always, do on the data, just to sort of see if there's anything there. Yeah. Yeah, but there's a lot of other, there's methods for trying to optimize the experimental design matrix, because if the different columns of the design matrix are not perpendicular to each other, then you'll get, you will sort of have a weaker ability to, if they're completely correlated with each other, then you don't have enough information to solve the problem. And so you can run your experimental design matrix through some software to try to optimize it and fiddle around with the columns so that with your when you show your different conditions, so that you get an actual matrix that has columns that are more perpendicular to each other, and so there are ways to just optimize your linear analysis. And then there's all different kinds of hyper complicated analysis where you have, what's happened is this is bad enough, what's happened is people have done things like we trained a neural network to listen to stories, and then we correlated the performance of the neural network with, some voxel in the brain or something like that. And so you end up with all these, so the neural network would be completely nonlinear. And so you have like some weird nonlinear model in the neural network.